Hello everyone, welcome to Probability and Statistics for Data Science. In this video, we're going to provide an overview of probability. The goal is for you to see how all of the topics fit together at a high level, not to provide specific details. So please don't worry if you don't understand something. It will be explained in the following videos, which will be focused on each of the topics. All right, let's get started. So the motivation to even define probability in data science is that it allows us to reason quantitatively about uncertain phenomena. What do I mean by uncertain phenomena? Consider the following questions. Who will win the next presidential election in the US? What will be the cost of a certain stock, for example, Tesla, tomorrow? Will the New York Knicks win the next NBA championship? These questions do not have definite answers because they each have different possible outcomes. Probability allows us to quantify how likely each of these outcomes are, and in general to reason in a mathematically sound way about uncertain phenomena like this. All right, so what is our strategy to define probability? Our strategy is to model the uncertain phenomenon that we're interested in as an experiment that could be repeated over and over and over and over. Okay? So for example, when we talk about the probability that the Knicks will win the NBA championship next year, what we mean is imagine that we repeated the NBA season over and over and over and over, then the probability of the Knicks winning would be the fraction of times that the Knicks would win among all of those repetitions. You might be thinking, but Carlos, the NBA season just will happen once. It won't happen over and over. And that's completely correct. This is just an abstraction, but it's an extremely useful abstraction that enables us to reason about this uncertain phenomenon. All right, so what is the plan for this video? First, we will describe probability spaces, which provide a mathematical framework to talk about probability and to define probability. Then we will cover conditional probability, which allows us to incorporate additional information to update probabilities. After that, we will explain how to estimate probabilities from data, which is of course extremely important in practice. And then we will cover independence and conditional independence, which are very important concepts in probabilistic modeling. Finally, we will talk about the Monte Carlo method, which enables us to compute probabilities using computer simulations. All right, so let's get to it. Probability spaces. When we define a probability space, what we do is we model the phenomenon of interest as an experiment based on this intuitive definition of probability that we already covered. And this experiment is going to have mutually exclusive outcomes. So it will have certain outcomes and they cannot happen at the same time. If we roll a die, it cannot be a 1 and a 2 at the same time. That's what I mean by mutually exclusive. Then what we do is we group the outcomes in sets called events and we assign probabilities to those events. Let's take a look at an example, okay, which is going to be this six-sided die that I just mentioned. The set of all possible outcomes when we roll a six-sided die is just the numbers that we can get, which are 1, 2, 3, 4, 5, 6. In general, we call the set of all possible outcomes the sample space of the probability space. In this case, this is the sample space. We usually use this big omega to denote it. So what are some examples of events that we could consider here? We could consider the event of rolling an odd number. This would be the event that contains the outcomes 1, 3, and 5. Another event that we could be interested in is rolling a 4. That's a very simple event that just contains one outcome, 4. Or we could consider the event we roll some number, which is equal to the sample space. Okay, that's also a valid event. All right, so within a probability space, we have a probability measure, which is just a fancy word for a function that tells us what is the probability of each of the events that we're considering. So this probability measure assigns a probability to each event. We're going to go back to our intuitive definition. What does this probability of an event mean? It means that if we could repeat the experiment over and over and over and over, then the probability would be the fraction of times that the outcome would be in the event. I don't know if you hear the ambulance, but it's New York City. It's never very quiet. Hopefully, it's not too loud. All right, so now based on our intuitive definition, we're going to establish 3 rules that probability spaces need to satisfy. Again, we're not going to go deeply into them. I just want to give you a taste of how we define probability spaces. We'll go much more in detail in the video on probability spaces. Okay, so what are these rules that this probability measure and in general the probability space needs to satisfy? Well, we need to assign a probability to the whole sample space. Okay, here we represent the sample space as this square. This is called a Venn diagram. In Venn diagrams, the probability of an event is equal to the area of the region that represents the event. So in this case, this square represents the whole sample space. Its area is equal to the probability of the sample space. It follows from our definition that the probability of that sample space should actually be equal to 1. Okay? Again, we're not going to go into details as to why, but you will see it in the separate video. So that's the first rule. We need to assign a probability to the sample space. That probability needs to be 1. It's the probability of something happening, so it kind of makes sense, I hope. Now, if we second rule, if we assign a probability to an event A, which we represent by this square here, we also need to assign a probability to the event that A does not happen. Okay? In set theory, if we take all the outcomes that are not in A, that's called the complement of A. Okay, we put a little C above. So we need to assign a probability to the complement. What should that probability be? We can reason with the Venn diagram. The big square has probability 1. So what is the area of this region here? It's 1 minus the area of A, and the area of A is the probability of A. So the probability of the complement should be 1 minus the probability of A. Again, this can also be derived from our intuitive definition. And finally, if we assign probabilities to 2 different events, we also need to assign a probability to the event that either of them occurs, which is the event that has the outcomes that are in A or in B. In set theory, that's called the union between A and B, and we've drawn it here in gray. We also need to assign probabilities to the intersection of both events. That's the event that contains the outcomes that are in A and also in B. This is the event here in gray on the right. If 2 events are disjoint, which means that their intersection is empty, from the Venn diagram we see that the area of the union should be equal to the sum of their individual areas, right? If this is empty. If this is not empty, then that's not true anymore. So for disjoint events, whose intersection is 0, the probability of the union should be equal to the sum of the individual probabilities. And again, this also follows from the intuitive definition. Why do I keep saying this follows from the intuitive definition, this follows from the intuitive definition? The reason why I keep repeating that is that the first time that you see probability spaces, they seem very intimidating. They seem a little scary. There's a lot of mathematical notation, like these axioms, you need to satisfy this, you need to satisfy that. But we're going to see that even though they might look very abstract, they're just a way of implementing the very simple intuitive definition of probability that we started with. Okay, and it's important to remind ourselves of that if we're getting a little bit overwhelmed by all the mathematical notation. All right, let's move on to conditional probability. To explain this example, this motivating example, I need to explain a little bit about the NBA. So in the NBA, you have a regular season where all the teams play each other. And then after that, the best teams in the regular season go on to play in the playoffs, and whoever wins the playoffs wins the championship. So now imagine that the Knicks are the best team in the regular season. Okay, they win the most games. If that happens, then we should definitely update our probability that the Knicks win the whole championship. And conditional probabilities allow us to incorporate information like that to update probabilities. So let's modify our intuitive definition of probability to obtain an intuitive definition of conditional probability. So remember, in our intuitive definition of probability, we're assuming that this uncertain phenomenon that we're interested in is repeated over and over and over and over. We're going to do that again. But now instead of looking at the fraction of times that the Knicks win, what we're going to do is we're going to just take the subset of times that the Knicks were the first seed, which means that they win the regular season. And we're going to look at the fraction of times out of those that the Knicks win the championship. And that's the conditional probability. Okay, so we take just the subset of repetitions of our experiment that are relevant, where whatever we're conditioning on happens, and then we look at the fraction within that subset. I hope that makes sense. From that, the mathematical definition, if you want, for conditional probability of an event B given A should be the following. And again, this will be clear, like explained in more detail in the video on conditional probability. The probability of B given A should be the probability of the intersection divided by the probability of A. Let's just provide a very quick justification in terms of Venn diagrams. So imagine that we have this sample space, which has these two events A and B, and now we want to condition on A. What does that mean? It means that we're just interested in these outcomes that are in A. We're not interested in the outcomes that are out of A. So what are we going to do? We're going to create a new probability space where A is the new sample space. And if you realize, the outcomes that have survived, that we're keeping, that were also in B, are exactly the ones in the intersection between B and A. So is the conditional probability the probability of the intersection? Not quite, because when we create this new probability space, we need to blow up the probability of A so that it equals 1, because it's the new it's a new sample space, and the sample space has to have probability 1. So we need to multiply by a factor of 1 over probability of A to ensure that that happens. So when we look at the probability of the outcomes in B that we're interested in, they get multiplied by 1 over probability of A. Since they're the outcomes that are in the intersection, we obtain exactly this formula. Okay, so that's a quick justification in terms of Venn diagrams for the formula of conditional probability. An important consequence of the definition of conditional probability, it just follows completely from the definition, is the chain rule, which says that the probability of the intersection between A and B is equal to the probability of A times the conditional probability of B given A. Another important consequence is the law of total probability. Imagine that we have a partition of the sample space. What is a partition? A partition is a group of sets that cover the sample space. Their union is equal to the sample space, and they are disjoint. They don't have any common outcomes. And now we're actually interested in the probability of a set of an event B, but we only have access to the probability of B given A1, B given A2, and B given A3. What can we do? Well, what we can do is we can separate B into 3 parts. So actually, here I'm going to have to write a little bit. The probability of, we separate it into 3 parts, okay? The intersection with A1, A2, and A3. And now each of these guys can be separated into, by the chain rule, into probability of A1 times probability of B given A1, probability of A2 times probability of B given A2, and probability of A3 times probability of B given A3. Okay, so we can combine all of these conditional probabilities, but we need to weight by the probability of each of the events in the partition. We sum them all together, that gives us the probability of B. That's the law of total probability. And you can see why, in general, I don't write a lot on slides, because my handwriting is pretty terrible. Okay, it's important to remember that the probability of A given B can be very different from the probability of B given A. Let's look at this visually. So remember that if we have this sample space here and we want to condition on A, what we do is we blow up A, and now the probability of B given A is the probability of the intersection divided by probability of A. Now if we want to condition on B, we're going to do the same thing, except that we're going to blow up the little circle. But when we blow up the little circle, the multiplicative factor is, so here the multiplicative factor is 1 over P of A, so that the sample space has, the new sample space has area 1. Here the multiplicative factor is 1 over P of B. And P of B is smaller, so this probability ends up being larger. Okay, so this gives you like a quick justification of why P of A given B is different in general from P of B given A. It just because P of A this happens when P of A is different from P of B. However, we can compute P of AB from P of B given, sorry, I said P of AB. Probability of A given B, the conditional probability of A given B, we can compute it from the conditional probability of B given A. But to do that, we need to reweight by the probability of A and the probability of B. Okay, and this is called Bayes' rule. All right, all of that is great. We have learned about probability, about conditional probability, some important properties of conditional probability, but in practice, how do we estimate probabilities? And that's something that it's important to understand. The sooner the better, in my opinion. Well, what we do is we go back to our intuitive definition. We say, okay, what does the probability of an event mean? It means that if we repeat the experiment a lot of times, that's the fraction of times that we observe the event. So what if we have a data set? For example, we observe 60 rolls of a die, and 8 of them are 2. How would you estimate the probability that we obtain a 2 with that die? Well, based on our intuitive definition, it should be 8 divided by 60. And that's, as I should have waited. Sorry about that. We already answered this question. And it's as easy as that. The empirical probability given a data set, the empirical probability of an event A is just the fraction of data points that are inside A. Here we have a little bit of a fancy way of expressing that. This thing here is an indicator function that is equal to 1 if the point is in A. But this is just the number of points that are in A. So we check how many points are in A, we divide by the total number of points, that's the empirical probability. As simple as that. Again, it's based on our intuitive definition of probability. What about conditional probabilities? How do we estimate those from data? Well, imagine that we roll the die 60 times and we observe 8 2s, 6 4s, and 10 6s. And now we want the conditional probability of the event rolling a 2 given that the roll is even. So because we want to condition on roll being even, we are only going to, based on our intuitive definition of conditional probability, we're only going to take into account the rolls which were even, which are this one, and this one. Conveniently, I haven't told you about the other ones. So the total number of even rolls is 24, if I'm not mistaken. Now we look at rolling a 2 and we see its intersection with roll is even. Every time we roll a 2, the roll is also even, so the intersection is actually pretty easy. It's just the number of times that we roll a 2. In this case, it's 8, and now we divide 8 by the number of times that we observe an even number. Okay, so it will be 8 divided by 24. I hope that makes sense. So a little bit more formally, if we have a data set and we want the conditional probability of B given A, we count the number of points in the intersection and divide by the number of points in A. As easy as that. Okay. All right, so now let's talk about independence. An event A is independent from an event V if, when we compute the conditional probability of B given A, it doesn't change. It's the same as the probability of B. And this will also imply that the probability of A given B is equal to the probability of A. In general, there's this condition that implies both of these things, which is that the probability, and this follows from the chain rule, the probability of the intersection is equal to the product of the individual probabilities if two events are independent. Conditional independence, I was going to just go on and talk about conditional independence, but I need to say something before that is quite important. Imagine that you have multiple events and they're pairwise independent. By pairwise independent, I mean A is independent from B, B is independent from C, C is independent from A, by the definition that I just explained. Does this mean that they're all completely independent? For example, does that mean that, now there's someone yelling in the corridor, I hope it's not too loud. Does that mean that the probability of C, given the intersection of A and B, is going to be equal to the probability of C? Which should happen, right, if they're all independent? Well, actually, the answer is no. So when we have multiple events, we need a stronger condition to ensure that all of them are independent. And this condition is that for any subset of the events, okay, if we take m of them, for those, it needs to happen that the probability of the intersection must factorize into the product of the individual probabilities, and this has to happen for any possible subset of the events. If that happens, then all of them are completely independent, and that we call mutual independence. All right, so now I think we can go on to talk about conditional independence. Conditional independence is essentially the same as independence, except that we're conditioning on a third event. Okay, so same thing, like A and B are conditionally independent if when we condition, just to be clear here, this means that we're conditioning on the intersection between B and C. Okay, just a notation, just to clarify notation. So if the probability of A given B and C is the same as the probability of A given C, then we say that A and B are conditionally independent given C. Very similar to independence, it's just that we're conditioning on C everywhere. This looks so similar to independence that you might be tempted to say, like, why are we making a big deal out of this? Like, maybe this is implied by independence or this implies independence. Well, actually, independence does not imply conditional independence. And conditional independence does not imply independence, and this is extremely important for probabilistic modeling. We will justify why in the video on conditional independence. All right, so now to motivate the last topic, I will tell you that life is not a homework problem. So this is something that kind of surprised me as a student, because I used to do all these homeworks where we were deriving probabilities. So it turns out that in real life, even if you have all the necessary information, it is very common that you will not be able to compute probabilities exactly. Let me give you an example of why. Imagine that we want to model some championship, like for example the NBA or Wimbledon or March Madness or something like that. We want the probability that a certain team wins the whole thing. And we're going to assume that we are able to estimate very precisely the probability that any team beats any other team. So we have all the information we need. It's just a matter of sitting down and computing the probability. Well, it turns out that to compute that probability, we have to take into account all the possible ways in which a team can win. And the number of ways scales exponentially with the number of teams. So unless the number of teams is very small, it's going to be completely impossible to go through all of those possibilities in a reasonable amount of time. Like, it would take years to do. So unfortunately, in even quite simple examples, even if we have all the available information, we cannot compute the probabilities that we're interested in. That's the bad news. The good news is that we can again go back to our intuitive definition of probability and find a solution. The solution is the following. Given that a probability at the end of the day is just the number of times an event occurs if we repeat our experiment many times, how about we just do that with a computer? Okay, for example, if we're interested in the NBA season, how about we just simulate the NBA season a few million times, and then we see how often the Knicks win. That actually works very well, and it's done in practice all over the place, and it's called the Monte Carlo method. So again, to approximate the probability of an event A, what we do is we simulate many outcomes using the information that we have, and then we count how many of those outcomes, what fraction of those outcomes are in the event, and that gives us a very accurate estimate of the probability of A, just by computer simulation. And again, this is super important in practice. And that's it. So let's summarize what we talked about. We've talked about probability spaces, which provide a mathematical framework to talk about probability or to define probability. We define conditional probability, which allows us to update probabilities using additional information. We explained how to estimate probabilities from data. We talked about independence and conditional independence, which are very important from probabilistic modeling. And finally, we described how to use computer simulations to estimate probabilities. As I said, the goal here was just to provide a quick overview of everything. So don't worry if some of the details were not clear. You can just take a look at the following videos for those details. And that's all I got. Thank you very much for your attention.